Okay, so I'm doing the introduction to our 5G presentation. 5G is the next progression in wireless network technology that will help provide the necessary infrastructure for the next generation of wireless devices, such as smartphones, Wi-Fi enabled gadgets, streaming devices, and much more. 5G wireless technology is still in its infancy, with much of its development and distribution of 5G networks still being implemented slowly across the globe. One of the main motivations for the development of 5G is that the rest of the spectrum of radio wavelengths in which the current 4G wireless network currently inhabits is quickly filling up due to services provided by telecommunication companies and the consumers these services are being provided to. Cost of implementing this infrastructure for 5G is going to be prohibitively expensive, but telecommunication companies are faced with little choice. 5G networking is being developed to meet a wide variety of use cases, both mobile and non-mobile.
1G revolution, the first generation of wireless mobile communication, began in the 1980s with analog communication. Analog included the mobile telephone communications and had transfer speeds of 1.9 kilobits per second. 2G, the second generation of wireless communication, began in 1991 and included voice calls, text-only SMS messages, and internet connection facilities. Transfer speeds of 2G were 10 kilobits per second. 3G began in 1998 and led to the smartphone revolution because 3G included capabilities of sending pictures and videos. That could be done because transfer speeds were at 2 kilobits per second up to 14.6 megabits per second. 4G, which is the standard now, began in 2008. 4G is also known as LTE, long-term evolution. It's our current standard, and it includes data-intensive apps such as video conferencing, gaming, and media streaming. 4G includes transfer speeds of 6 megabits per second. All of this leads up to 5G. 5G revolution, the fifth generation of wireless communication, began in 2019. And its transfer speed is 1 gigabit per second up to 60 gigabits per second. The 5G mobile revolution will have several mobile application advantages. 4G included 60 megabit per second speeds of transferring data. 5G will begin at 1 gigabit per second. 5G will have a much bigger transfer speed advantage. The other advantage is speed advantage is latency. 4G has an average latency, which is the connection speed of 50 milliseconds. 5G's average latency will be 1 millisecond. The increased connection density of 5G is another big advantage. 4G included 2,000 devices could be connected within a 0.38 square mile section. 5G will connect up to 1 million devices within the same area of 0.38 square miles. Another 5G mobile application advantage is precision. Because 5G uses shorter wavelengths, the precision is increased for GPS mobile applications. 5G is also said to will also increase battery life because of the increased reduced latency and increased data speed transfers. Because data is being transferred faster, the battery life will be longer because less battery will be used. And finally, 5G will just inspire more uses and improve existing uses of mobile applications because of those advantages, because of better precision, faster transfer speeds, and lower latency. So those advantages will improve mobile websites because mobile websites will download and send data much faster. The mobile websites will include much more data-intensive media content. Because of the increased connective density, the Internet of Things will expand. The Internet of Things was kind of inhibited by 2,000 devices within that 0.3 square mile section. And at 1 million devices, we'll see a huge expansion. Predictions 28 billion devices by 2021. Another 5G mobile application use that we'll see improving is mobile gaming. Again, with faster latency and faster data transfer speeds, we'll see, again, better graphics and more streaming games. And the precision, the improved GPS precision will improve drone technologies that use 5G GPS. So, want to get more information, there is a website listed at the end.
So I'm going to be talking a little bit about the development of 5G and some of the technological applications that's being implemented with 5G technology. With the first slide here, it's over the 5G spectrum, which 5G operates at various levels of the radio wavelength spectrum. Different parts of the spectrum offer different features. 5G wireless networking takes advantage of the low, mid, and high-end bands of the available radio wavelength spectrum. According to Sasha Segan of PCMag, there are three main kinds of 5G: low band, mid band, and high band. The low and mid band frequencies have been utilized with previous networks, but what 5G aims to capitalize on is that previous generations of networks have not utilized the high band frequencies. The high band frequencies utilized by 5G networks are referred to as millimeter wave signals. These millimeter wave signals are the frequency bands that 5G is advertising that will provide download speeds far and above what 4G can provide. The trade-off with these millimeter wave signals is they are far weaker when traveling across larger distances. These millimeter waves are much more easily obstructed by walls, landscape features such as trees or other obstructions in the environment. So while these millimeter waves are capable of much higher speeds in the high band spectrum, essentially they can only travel shorter distances to provide these speeds. The main drawback with the implementation of 5G networks is that at this point, they have only been effectively distributed in larger cities. The shorter distances that these millimeter waves can cover require many more access points to be installed throughout a smaller area, so the high band signals provided by 5G don't have to travel as far and therefore can achieve the gigabyte speeds 5G advertises. Similarly to the spectrum that filled up prior to 5G's inception, making 5G necessary in the first place, 5G's higher band frequencies in theory will also fill up over time, as did the 4G mid-band frequencies. So eventually in time, though it may not be on the foreseeable horizon quite yet, 5G's frequency spectrum will fill up and require an additional spectrum to be added for further use with either future 5G networks or 6G networks and beyond. 5G is an evolution of networking as virtualization offers an exponentially larger amount of network traffic to travel over the same existing hardware network that already exists without needing a complete physical overhaul of the network. Key hardware functions will become part of cloud computing. These essential network functions will become software applications. Spectral efficiency refers to how many bits per hertz can be sent through a given amount of spectrum. 5G networking technology employs various technological upgrades such as signal optimization and multiple in, multiple out antennas to allow more data to be sent through the part of the radio frequency spectrum the network is using. It is also worth mentioning that there is no exact agreed upon definition of what or how 5G networks and technologies are being introduced. Different companies such as Verizon and AT&T are developing their networks separately and in totally different manners than one another. The same can be said for countries. The United States and China, for example, are going about developing their 5G networks, and again, vastly different methods. Verizon until recently has been focusing on the millimeter wave frequencies discussed earlier that offer the highest speeds but are not able to traverse longer distances easily or nearly as well as the low and mid band frequencies can. While Verizon has been focusing primarily on the high band spectrum of the 5G network, AT&T has been focusing more on the low and mid band frequency spectrum for their 5G network. When it comes to the different approaches countries themselves are taking to implementation of 5G networks, in reference to China Tower, a Chinese state-owned cell phone tower operator, Julia Horowitz of CNN Business says that in 2017, they added roughly 460 cell sites per day, while the United States has less than 5 cell sites per 10,000 people. One of the applications of 5G that is perhaps the most intriguing currently is that it will bring about a new era for the Internet of Things, or IoT, with devices in the household ranging from refrigerators, televisions, thermostats, security cameras, and now driverless vehicles making their way to the market, and many more devices as well. The need for these devices to be able to instantaneously communicate over the internet is more important than ever. According to Alan Seal's article from vxchange.com, 4G currently offers speeds topping out around 12.5 megabytes per second, while 5G approaches up to 2.5 gigabytes per second. With speeds like that, devices connected to the internet will be able to send data and communicate with connected devices almost instantaneously, which will be crucial for the future development and use of IoT. Smart cities and driverless cars are two of the primary technologies that aim to benefit the most from the upgrade to 5G. These technologies are perfectly suited for the ultra high capacity and low latency networks that 5G will provide. Those features of 5G will also be necessary for immediate communication these systems will need to operate. With small cell sites employed in larger cities on everything from street lights, traffic lights, buildings, and roadways, machine vision and machine learning will be possible for the driverless vehicles in smart cities. With the ability to communicate with other driverless vehicles, IoT devices, and cell sites virtually instantaneously, the integration of these technologies into daily life will make for an even more seamless transition. These technologies will be able to learn and react in ways not possible with 4G due to its inherent limitations. This does not mean 4G is bad or disappearing in any way anytime soon, as 5G networks will still need to work on top of existing 4G infrastructure for some time to come. Lastly, here for this slide, another possible arena that 5G could level the playing field in is the realm of cable service providers. Cable television has exclusively been the domain of companies such as Comcast or Charter or Dish Network, but with the speeds and the amount of data that can be sent over the frequency spectrums 5G will occupy, wireless phone carriers such as Verizon and T-Mobile are offering their broadband services as viable alternatives to traditional cable companies. Verizon, for instance, provides speeds between 300 and 840 megabits per second in comparison to Cox, the third largest US cable provider, who sells its residential 300 megabytes per second product for $79.99 per month. The only catch with these cell phone providers providing speeds at these rates is that, as was mentioned earlier, Verizon specifically makes use of the millimeter wave portion of the radio frequency spectrum. The millimeter waves can only travel very short distances between small cell sites, and so far have only been implemented in large cities, as has been previously stated before in my presentation. So while Verizon could previously possibly become a player in the cable service industry, it will most likely be limited to larger cities for the time being. But the possibility of a broadband service being able to compete with the traditional cable company is another example of technology 5G has made into a realistic possibility.
5G wireless networking represents the next big transformation in mobile networking. Unlike its predecessor 4G, which sought and succeeded in connecting people by providing Internet of Things capability, 5G wireless technologies is looking to connect everything by utilizing IoT optimization. Because of this, a wide spectrum of band frequencies is needed to meet the requirements for 5G to deliver its capabilities. 5G offers a spectrum range of anywhere from 400 MHz to 90 GHz, with different ranges of the spectrum providing various combinations of coverage and transmission speeds. These areas of the spectrum are broken into three categories: low band, mid band, and high band, also known as millimeter wave. The low band spectrum contains frequencies below 1 GHz that have the capability to provide hundreds of miles of coverage. While the amount of coverage provided by low band frequencies is substantial, the speed at which information is transmitted is slower than the speeds provided by higher frequencies. The transmission speed of a low band frequency puts out anywhere from 30 to 250 megabits per second on average, with 5G capabilities reaching a peak of around 250 megabits per second. Low band frequencies are also better suited at being able to travel through objects, reducing the effects of attenuation. The mid-band spectrum contains frequencies between 1 to 6 GHz and can provide several miles of coverage as well as an additional network capacity. The amount of coverage and the transmission speeds of mid-band spectrum fall between low-band and high-band frequencies. In particular, the transmission speeds of the mid-band spectrum peak at an average of about 2 gigabits per second. Mid-band spectrums can be considered as the sweet spot for 5G wireless technology due to its reasonable coverage and more than satisfying transmission speeds. Many frequencies that were allocated to previous generations of wireless technology are being reclaimed or refarmed for intended use with 5G. This is also a part of the spectrum that is implemented most globally. The high band portion of the spectrum, also referred to as millimeter wave, provides the highest transmission rates at the cost of smaller coverage area and high susceptibility to propagation issues. This portion of the spectrum falls roughly within the range of 20 GHz and above. The speed provided by 5G millimeter wave can be tens of gigabits per second, but individuals more realistically see exchange rates of up to 3 gigabits per second. Because of the limitations of millimeter wave, it is projected that it will be mostly provided in dense urban areas such as stadiums, coliseums, or town squares. Although these restrictions currently prevent the majority of the population from receiving all that 5G has to offer, advancements in antenna technology are increasing the range at which millimeter wave frequencies are able to travel. In order to combat the various propagation challenges presented by millimeter wave, a method is used which forms and/or steers these radio signals to users. Beamforming serves as a way to increase the performance of mobile networks by providing increased capacity for base stations, reduced power usage, higher quality signals for receivers, and reduced spectral interference. These benefits only represent a portion of ways that beamforming provides increased wireless network performance. Beamforming is utilized by transmitting the same signal through multiple close proximity antennas at different intervals to create a single directional signal. This in turn gives the capability to point a signal in a desired direction. Beamforming is a concept that has existed for almost 80 years, yet it plays a major role in bypassing some of the limitations presented by 5G, particularly the limitations imposed by high-frequency wavelengths. In order to send multiple overlapping signals, beamforming employs the use of multiple input, multiple output, or MIMO antennas. MIMO refers to the transmission of packets from the multiple antennae of a sender to the multiple antennae of a receiver. By sending and receiving multiple transmissions of the same signal, the effects of a decreased signal-to-noise ratio and an increased bit error rate as a result of fading and multipath propagation can be mitigated through the process of reconstructing the original transmission from the signals that are received. Other benefits provided by MIMO systems include, but are not limited to, a higher throughput, reduced packet loss, and an increased signal strength that is not dependent on line of sight between sender and receiver. Similar to techniques mentioned in the previous section covering beamforming, spatial multiplexing is a technique implemented by MIMO systems to increase the amount of data flowing through a channel without having to increase the channel's bandwidth. Spatial multiplexing utilizes the number of antennae on a MIMO system to transmit separate streams of data that converge within the same spatial frequency, creating an amalgamation of separate transmissions. This combined transmission is then separated by the receiving MIMO system. Space-time coding is another mechanic used by MIMO devices to transmit data that would normally be sent using one antenna over multiple antennae. This allows for gain adjustments to be made, resulting in better bidirectional communication. The concept of massive MIMO is an extension of MIMO that is used to maximize throughput and spectral efficiency by increasing the number of antennae housed on base stations while taking three key factors into consideration: beamforming, spatial multiplexing, and spatial diversity. Spatial diversity is a term that refers to the amount of available space for signals to traverse without interfering with one another. The amount of spatial diversity is dependent on the placement of the many antennae on a massive MIMO base station. The effective use of multipath propagation in correlation with spatial diversity varies depending on the vertical or horizontal placement of the antennae relative to each other. By increasing the number of antennae on a base station, the effects of beamforming are enhanced by increasing the strength, distance, and precision of a transmission. This in turn creates a stronger signal for users without increasing levels of interference. More antennas result in narrower beams and increased array gains. Overall, the benefits of massive MIMO implementation include improved coverage and increased network capacity. Even at the cell's edge, the increased array gains from adding additional antennas allows users to experience high data rates, and those positioned closer to the base station will see a further increase of data rates. Users on the move will also benefit from improved coverage, as this coverage can be adjusted through the use of beamforming capabilities. The number of users that can effectively receive the expected level of data exchange rates increases as the number of antennas on a massive MIMO base station increases. These services provided by massive MIMO contribute to an overall increase in user experience. Wireless networking continues to significantly change the way we live our lives. With the assistance of older and emerging technologies, we are getting that much closer to attaining all that 5G has to offer. By expanding into millimeter wave, a much higher network capacity is provided. High data exchange rates and a much lower latency provides a better experience for users. Also, the potential implementation of 5G goes way beyond that of mobile networking. Soon, city infrastructures, factories, commercial and residential broadband services, and even autonomous vehicles will be transformed using emerging 5G technologies.